Privileged to help Dennis celebrate his 60th birthday. I've known Dennis, I don't know for how long. For one thing, I recall back when I was an undergraduate seeing this bunch of lecture notes called, I believe, Geometric Topology, published by MIT, which I tried to read, and it sounded at the time like the works of a visionary, so something like a mystical writing about mystical objects. And I tried to read them, and perhaps I succeeded to some extent. I probably succeeded almost as well as anybody. But then I met Dennis. I guess it must have been first around 1980 or something. At the time, I had started making pictures of Newton's method to solve cubic polynomials. And my gosh, they sure seemed awfully mysterious. And then I went to see, I went over and brought them to IHES. And it was just fantastic. There was this whole subject that had already been developed, that had been developed by Fatou and Julia ages and ages ago, which I didn't know about at all. But Dennis knew all about it, and it taught me my whole subject. So he sort of, and then he proved the main theorem of the subject. So what can I say? Dennis had an absolutely determining effect on my own mathematical career. He taught me and knew all about the field that I have been studying ever since I started on this. And, well, it's just wonderful being able to talk about the extensions of what he taught me.
Why didn't you ever tell me this before?
I thought you knew it. It never occurred to me that you could have thought you had a less influence than you actually did. This picture had better not disappear on me. Okay, so what I want to talk about today is, well, not just today, what I want to talk about in all four of these lectures is, well, of course, the object is understand dynamical systems. So the name of the game is, how do we understand dynamical systems? Which fundamentally means, how does one bring dynamical systems down to some kind of combinatorial model? And the final, I mean, I'm not claiming that this is the final answer to the question, but at least in higher dimensions, in dimensions 2 or higher, I should say, higher dimensions means more than one. In higher dimensions, the procedure that I am going to be proposing is a procedure of doing infinitely many blow-ups to try to understand what is happening at infinity for the dynamical systems that I'm going to study. However, I think that it's a good idea to bring out the one case of dynamical systems in one dimension where we really do have a combinatorial model of what we are seeing. And then to try to show how I am trying, by these infinitely many blow-ups, to build an analogous procedure in infinitely many dimensions, which hasn't perhaps been 100% successful yet. But, well, we'll see what I can do. So, the great success story of dynamical systems in one variable is the story of iteration of the polynomials, of the quadratic polynomials. And for these, we really do have a combinatorial model which describes just about everything about them. This is due largely to a wonderful theorem of Fatou's, which says either, well, before I write down anything, let me say that the fundamental object when trying to understand this is the set KC is a set of z such that the sequence z, p sub c of z, p sub c iterated twice of z, and so forth, is bounded.
Is z the Grossman number?
That's actually not such a ridiculous question. It is emphatically not a Grossman number, and in my mind, it's a complex number, and that's where the success story lies. But one can certainly take c and z to be real, and I would like to point out that much of the success in understanding real one-dimensional dynamics has been to begin by studying things in the complex. As it turns out, the real locus is exceptionally complicated, and one learns a great deal about the real polynomials by creeping out of them, at them from the often much simpler complex world. But it would make perfectly good sense to let C and Z be n by n matrices, real or complex. It would make perfectly good sense to let them be quaternions. It would make perfectly good sense to have them be in some Clifford algebra. It would make perfectly good sense to have them be in the algebra of bounded operators on a Hilbert space. Every one of these is a perfectly interesting problem, but as far as I know, the only ones that are actually understood in any serious sense are when C and Z are complex or real. And so those are the ones that I'm going to focus on, which doesn't mean for a second that the others aren't interesting. It's just that we haven't been so successful in understanding them. There's actually been a non-trivial amount of work on the case when C and Z are both quaternions. But this work has not resulted in any really outstanding breakthrough, largely because the issue of what it means to take the derivative of a quaternionic map, it isn't even really crystal clear what it means to be quaternionic real, and quaternionic linear. And then it isn't crystal clear of what it means for the derivative of such a polynomial map to be quaternionic linear. I mean, quaternionic linear, you have to worry about whether it's linear on the left or on the right, and then the derivative turns out to insist to be a little bit of both, and then things don't work so well. In any case, there is this wonderful theorem of Fatou's, which says that there is a dichotomy. K sub C is connected if and only if 0 belongs to Kc, and a Cantor set if and only if 0 does not belong to Kc. Which naturally leads to a decomposition of the parameter space into two sets. M, the Mandelbrot set, is equal to the set of C such that K sub C is connected. Which is also equal to the set of C such that the sequence 0, C, C squared plus C, C squared plus C, the whole thing squared plus C, is bounded. Now, one cannot overstate how wonderful it is that we know what question to ask about a parameter value. Namely, the question to ask about C is Kc connected? And one cannot overstate either how wonderful it is that we know how to answer the question. Namely, you iterate this sequence, and if it's bounded, then you know by testing whether its absolute value ever gets bigger than 2, for instance, whether the answer to your question is yes or no. In all higher dimensional systems, we don't know what question to ask, and then even if we know what question to ask, we don't know how to answer it. Now, this isn't quite true. Much of today's presentation is going to concern how do you answer what is the analogous question about Hainaut mappings, and how do you answer them? And I'm going to try to give some sort of a coherent answer to that in the specific case of Hainaut mappings. But it's immensely more elaborate to both ask the question and to answer it. Well, perhaps answering it is harder. Asking the question isn't so hard. You had better not disappear on me. Yes. Okay. So the picture that you see in front of you here is a picture of M. So it's a picture in the C-plane, and for every point in M, you can go click at that point and see, hello, and see the corresponding picture of KC. So that one was connected. This one, I'm going to click at a point where I am not in the black locus. You see something which is a rather pretty Cantor set. You can go click here, and you see something connected. You can go click here, and see something which is also connected in some more complicated way. One thing that comes out of this is that the various pictures of KCs, even when they are connected, are quite complicated objects, but that they appear to have a certain combinatorial structure. And let me try to bring out what I mean by combinatorial structure. So let me erase the pictures that I've been making and then make a few in a more controlled fashion. Here is an archetypal picture. You don't actually have to keep it in mind because I'll bring it up again for a moment. But there is a certain archetypal picture. It corresponds exactly to the polynomial z squared minus 1. The place where I had gone click was in fact right at the point minus 1 of this picture. Minus 1, minus 1, minus 1, minus 1, minus 1, minus 1, there. Well, no, that's too, the imaginary part was too big. Minus 1, minus 1, minus 1, and 0. About there. Yeah, there it is. Here is, I'm going to give you a detailed description of this one in a moment. Here is another archetypal picture, otherwise known as the rabbit. Now, kind of thing that I want to bring out is what I mean by it has a combinatorial structure. So the specific combinatorial structure that I'm going to show you are ways of mixing these two pictures. One way of mixing these two pictures is to go here. Now what you should see is that I took my rabbit picture, and I replaced every copy of the body of the rabbit by the tower picture. And that is what you are seeing. You could also have taken the tower picture. You could also have taken the tower picture and replaced every copy of the body of the tower by a rabbit. This time, you started out with the tower picture. Oops, I want to make that one in white. Well, it's a little bit elaborate, actually, to draw this whole thing. So that thing's supposed to grow over to there, and then you have another rabbit inside there, and so forth. Okay, so you have these two pictures. You can meld them. You can meld them in two different ways. What is the underlying scheme for understanding what is going on in these pictures? What exactly does it mean to replace one picture by another? What is the combinatorial structure? The combinatorial structure of these things has come out from understanding the external angles. Understanding the external angles means the following. A theorem, probably more or less also due to Fatou, says that given such a map P sub C with C and M, there exists a map phi sub C from C minus Kc to phi C minus the closed unit disk, having the property that phi sub C of P sub C of Z is equal to phi sub C of Z squared. It is the conformal mapping of the complement of K sub C in the Riemann sphere has this miraculous relation with the dynamics. And this contact of conformal mapping with dynamics is really the reason for which complex dynamics turns out to be a branch of complex analysis rather than a branch of dynamical systems. It's this rigidity, the fact that conformal mapping is what does what does the replacement for you, which really makes complex dynamics at the very heart of holomorphic dynamics in one complex variable. And of course, the fact that we don't have conformal mapping in two dimensions is a serious drawback to that field. So let's see the kinds of things that this gives you. Here are our towers. The polynomial is z gives z squared minus 1. The fixed points are alpha is equal to 1 plus the square root of 5 over 2, beta, and alpha is equal to 1 minus the square root of 5 over 2. They are respectively here and here. And phi gives you polar coordinates on the outside of this picture. One other way of imagining them, which follows immediately from the conformal mapping view, is that you can think of taking this object, charging it with electrons. If you make it out of a conductor, the electrons will go wherever they want. You know, the electrons, they hate each other, so they're going to go as far away onto the edges as they can. They'll settle down in the equilibrium distribution, creating a field on the outside which has equipotentials. And field lines. And the name of the game is figure out what field line goes where. Well, here is the zero field, the field line at angle 0. And here is the field line at angle 1/2. In this case, because we're iterating, in all cases, the intelligent thing is to measure angles in turns. 1 turn, 1/2 turn, 1/4 turn. Multiples of pi just get in the way. Now, okay, 1/4, 3/4, those are fairly easy, but how about this one? This is a fixed point, and therefore the field line that goes to it is tethered at that point. It can only map to another field line that maps to the same point, and we can go and ask the computer what really happens near there. Well, you can see that what happens near there is that things map from here to there, back to there, back to there. So this ray maps to this one, and this ray maps to this one. But this ray is at a certain angle theta. According to this rule, this one is therefore at angle 2 theta. It mapped by squaring. Squaring doubles the polar angle, which maps back to the one at angle 4 theta. So the angle theta is an angle theta which satisfies that theta equals 4 theta, or 3 theta equals 0, but we're counting mod 1. So the only choices are 1/3, 2/3, and 0. 0 is already taken. So it seems clear that this one has angle 1/3 and this one has angle 2/3. After which this one, which is an inverse image, has angle 1/6. And this one has angle 5/6, and then this one has angle 1/12, and this one has angle 11/12, and then, well, and so forth. And what I really want to bring out of this is that a combinatorial model for KC has been built. And this combinatorial model consists of drawing in the curves joining the angle at 1/3 to the angle at 2/3, and the angle at 1/6 with the angle at 5/6, and the angle at 1/12 with the angle at 11/12, and the angle at 5/12 with 7/12, and then, as it turns out, 5/24 and 7/24, and so forth, and collapsing down the rays that have been drawn. Okay, so there is a mathematical model, a topological model of how to build KC out of combinatorial data. As it turns out, there's something analogous for just about all KCs where C is connected. There is trouble when KC is not locally connected. KC is often locally connected, but unfortunately it's sometimes not locally connected. And actually, we don't have any very good idea of how KC is built when it's not locally connected.
Can you start with the complex structure?
In this case, no.
Could you repeat the question?
The question is, can I recover the complex structure from the combinatorial structure? And in this case, the answer is no, because there's complex structure on the inside. And well, maybe the answer is yes. It depends how much you're giving me. As it turns out, for instance, those external rays which land on the boundary of this component are precisely those which, written in base 2, can be used, well, in base 4, can be written using exclusively the digits 1 and 2. So, written in base 2, that means that you can write them as something like 0.01, 01, 01, 10, 01, 10, 10, 10, using only the digits which in base 4 would be 1 or 2, and which in base, wait a minute, yes, and which therefore in base 2 are only the combinations of digits 0, 1, and 1, 0. Now, given such a thing, you can obviously make a number in base 2 by replacing 01 by 0 and 10 by 1. That gives you a parametrization of the boundary of this component. Namely, you look at those sequences which use only 01s and 10s, do this bizarre trick like Cantor of taking the numbers in base 3 that use only the digits 0 and 2 and then replacing the 2s by 1s and thinking of it as a number in base 2. Well, you do the same thing. You take the numbers which in base 4 can be written using only the digits 1 and 2, replace the 1s by 0s and the 2s by 1s and think of it as a number in base 2. That gives you a circle's worth of angles. A rigid circle, glue in a disk according to that circle. Glue in other disks according to something analogous that you can build in a similar way. Takes a bit of doing to say exactly how. You then will build something which is topologically a sphere, and which has a complex structure both on the outside and on each component that you've glued in. Is there a unique complex structure which extends those? Answer, yes. So, in that sense, yes, you can reconstruct the complex structure from the dynamic. In other cases where there isn't any interior to KC, and you just have some sort of a dendrite, then in many cases the combinatorics completely determine the complex structure. You have a dendrite which is thin enough so that any analytic structure on the outside of it which is continuous on it or extends uniquely analytically. So yes, the answer is many times you can, and then when these things aren't locally connected, life becomes harder. What? For dendrites, yes. The conjecture is that for dendrites it's always true. But for things that aren't locally connected, I don't really know. What? Yeah, I mean, removability is, I mean, when you start putting in compatibility with the dynamics, then things go better, of course. Okay, now, if you look at the coloring that there is in this picture, the coloring is done in the world's stupidest way. Namely, well, the whole thing is done in the world's stupidest way. You start with some point in the complex plane, you iterate, and check if you ever get big. If you never get big, or at least if you haven't gotten big after 100 iterations, you leave the point in black. If you are going to get big, then on the last move where you get big, the imaginary part is positive of the place where you are is positive or negative. Color in red if it's positive, and green if it's negative, and that's the picture you get. But you will observe that if you go down this path here, if you go down this path, Then you go through green, red, green, red, green, red, green, red. And if you think about how to write this number 1/3 in base 2, you will observe that that is written 0.01, 01, 01, and so forth. Which means that if you translate this language of greens, reds, and so forth into changing the greens to 0 and the reds to 1, you can read off the external angle of any point by looking through what sequence of colors the corresponding ray goes, going down to that point. For instance, if we go back to the rabbit, now to get to this particular point, you go red, red, green, red, red, green, red, red, green, red, red, green, which makes you think that that external angle, the external angle of that ray might well be 0.001, 001, 001, which just happens to be 1/7. And yes, that's right. Now, the miraculous thing about this is that it works also in the dynamical space, in the parameter space. In the parameter space, so here I had an assumption. You have a polynomial p sub c, c is in M, then there exists a map from c, phi sub c, from c minus kc to c minus d bar, such that this is true. In any case, if c is not in M, there still exists phi sub c, from c in a neighborhood of infinity to c in a neighborhood of infinity, such that phi sub c of p sub c of z is equal to phi sub c of z squared, and c is in the domain of phi sub c. You can extend phi sub c down until c is in the domain, and then you can't extend it down until 0 is in the domain. You can't get it down to 0. So you can look at the map, capital phi of c is equal to phi sub c of c. And the theorem asserts capital phi from c minus m to c minus d bar is an isomorphism. What? Yes, is an analytic isomorphism. Which means that we can again take M and so forth, and draw in. In other words, this map, phi, is the conformal mapping of the exterior of the Mandelbrot set. And there are equipotentials and field lines and I can give you the associated angles. Of course, no one will be surprised at seeing 0 here and 1/2 here And already the question of 1/4 is a little bit more delicate. And here is 1/3, and here is 2/3, and here is 1/7, and here is 2/7, and then 3/7. 3/7 goes to the cusp of some little almost cardioid that one sees down on the real axis. Actually, this point is precisely the point minus 1.75. And then, for instance, 1/15 and 2/15 and 3/15 and 4/15, and then 5/15 is 1/3, 6/15. 7/15 goes to some even tinier little guy down here. And then 8/15, and so forth. Now, there's some extraordinary numerology, which is really explained by the sort of self-referential element in phi sub c of c, which is that the digits in base 2 of a given number reflect the dynamics at the end of the polynomial at the end of a ray with that particular angle. For instance, in this region, there is a periodic point of period 3. And the number 1/7 written in base 2 is 0.001, which repeats with period 3 also. And 1/15 is written 0.0001, which repeats. And inside here, there's an attracting cycle of period 4. Inside here, there's also an attracting cycle of period 4, which is why these numbers are also 15ths. Okay, the success story, which I don't want to go into any much greater detail than I've already gone into, about why we understand the Mandelbrot set. There is underlying this evidently a scheme for making a combinatorial model of the Mandelbrot set, which has still not been proved to be correct, incidentally. But there is an underlying scheme which you can think of taking a circle and drawing in the line joining 1/3 to 2/3, and then the line joining 1/7 to 2/7, and 3/7 to 4/7, and 5/7 to 6/7. And continuing this way, actually, if you take the numbers of the form p over 2 to the q minus 1, which you'll observe 3 is 1 over 2 squared minus 1, and 7 is 2 cubed minus 1, so the next ones to do are the 15ths. And if you systematically draw in next the 15ths, and connect each 15th to the next 15th that you can connect it to without intersecting what you've drawn so far. So you connect 1/15 to 2/15, and 3/15 to 4/15, and wait a minute, the next one is 6/15. You can't connect it to 7/15 because you'd have to cross this line, so you connect it to this one down here. This is 6/15, 7/15, 8/15, and so forth. These 2 points are actually much closer than I drew them. I didn't quite get my angles right. And you keep doing that next for the 31st, and then for the 63rds, and then for the 127ths, and so forth. And you look at the closure of the equivalence relation that you get on the unit circle. That should conjecturally be exactly the identifications that you get on the outside of the Mandelbrot set. So maybe it's worth writing that down explicitly. Connect the p over 3, then p over 7, then p over 15, and so forth, always to the next that you can connect it to without intersecting what is drawn so far. Now, define an equivalence relation by deciding that two things are equivalent if they are connected by a line, and then take the closure of that equivalence relation in the circle cross the circle. Consider the closure of the equivalence relation on R mod Z, where P over 2 to the k minus 1 is equivalent to P2 over 2 to the k minus 1 if they are connected by a line. Conjecture. Phi from phi inverse from C minus the closed unit disk to C minus M extends to a map from the boundary of the closed unit disk to the boundary of M. Maybe I'll call it gamma sub m, and gamma sub m of T1 is equal to gamma sub m of T2 if and only if T1 is equivalent to T2 by this equivalence relation. Now, that conjecture is exactly equivalent to proving that M is locally connected. This is exactly equivalent to the Mandelbrot set is locally connected, which explains why it is that that conjecture really is essentially a complete description of what happens for quadratic polynomials. It tells you exactly how the parameter space is built combinatorially. And a lot is known about MLC due to the efforts of many people, such as Yokos and Misha and Shishikura, Swiatek, many others. But this is still not proved, and stands as far as I can see as the big conjecture in the field of one-dimensional dynamics, or at least one of the two.
Is it also true the complex, if this were true, would the complex structure also be given until that procedure?
Absolutely.
That would also be true?
Yes.
There's no
There's
conditionality?
Can you announce what's absolutely true?
what's absolutely true. This map, phi inverse, extends to the inverse image of those polynomials that are not infinitely renormalizable. And that's a lot. It corresponds certainly to a set of full measure in the boundary of the circle, and we know combinatorially how to describe those angles as numbers in base 2 satisfying some properties. And two such angles are mapped to the same point if and only if they are equivalent in this sense. And okay.
You know how to rebuild the embedding of the natural set in the complex plane.
Yes. If this is true, we know how to rebuild the embedding of the Mandelbrot set in the complex plane by, I mean, after all, nobody could say that this equivalence relation is complicated. Well, at least not complicated to describe. The notion of closure is a pretty wild sort of thing. And it can be difficult to understand just exactly what happened in a closure. But if it is true, we know how to describe things completely, yes. Okay, so that is what I was proposing to say on the subject of one-dimensional dynamics. Now let me see, this lecture started at what time? It started at 11, didn't it? Quarter two. So I've got another 15 minutes. Okay. 10 minutes, at least. What? 12 minutes. Okay. Now, maybe the best I can do for right now is to try to just say that we would like a similar description for Hinel mappings. Hinel mappings are maps that are written as follows. H of xy is equal to p of x minus ay x. There are many forms, but this is my favorite. P, a polynomial of degree d greater or equal than 2, and very often p of x is equal to x squared plus c. X and y are two complex variables. This is a map from C2 to C2, which is very unlike p from some points of view, at least if a is different from 0, h inverse of xy is given by the formula y, p of y minus x over a. So it's invertible. But on the other hand, and this is part of why I write these maps in that form, when a goes to 0, this map is xy maps to p of x, x, which just says that the second coordinate isn't doing anything. And what's really happening is that you're iterating the polynomial p. What one would want to do is to have something similar to the Mandelbrot set and a description of the dynamical objects in terms of external angles and so forth and so on. And part of what I want to say is that we're getting there. It's not a complete disaster. There actually is a description of many sets, many of the dynamical sets in terms of external angles, and I'm proposing to explain exactly how this is done. It's, of course, nothing like as complete as the one-dimensional picture, but at the moment, I'm pretty optimistic. Maybe I will start by running my computer program and drawing K sub c's and drawing parameter space pictures for the Hinel map. And then, well, that will keep people, that will make people think twice about not coming to my lecture tomorrow when I explain exactly what it is that's being drawn and what those pictures really mean. I mean, I just don't have time If I start doing the theory now, I just won't have time to I won't have time to run the program. And I think the program conveys some information even in the absence of a precise description of what's going on. So I'm going to be talking about this case where the parameters are this number A and this number C. Now, I don't know how to draw in two complex dimensions, i.e. in two real dimensions. So instead of doing that, I'm going to take slices, two-dimensional real slices, or more exactly one-dimensional complex slices. And just at the moment, here is my window which opened up and says, what slice do you want to explore? And you can see it's chosen. I'm going to explore the C-plane for the particular value A equals, maybe I'll take a different one. Maybe I'll take 0.3i. No, maybe I'll take 0.3 plus 0.3i. Nobody's ever looked at this one before. Brand new. And it's going to make me a picture. And unfortunately, this picture reflects the fact that we don't know how to draw and what to draw in parameter space. So it comes up blank. Well, what do you expect? You don't know what you're going to ask, so it comes up blank. So I go click someplace in it, and it has drawn something. And the something that it's drawn is in fact a representation of an unstable manifold of a saddle fixed point, but you'll have to wait till tomorrow till I give you the full details of that. I'm now going to choose a critical point of some function or other, which is sitting on this plane. And there's an obvious critical point, for instance, right there. And you know what? It started drawing something in the parameter space. And maybe I'll make a blow up of the obviously significant part of this. Now, the particular value of A that I was using was 0.3 plus 0.3i. Which isn't all that close to 0. So you wouldn't really expect to be seeing anything that is too similar to the Mandelbrot set. But maybe you see a cusp there. Maybe you see something over here which makes you think that it might be rather like maybe the 3-ball. Maybe it's some analog of the 3-ball. And I tell you what, we can go click and find out what there is there. So let's go click here. And you know, maybe this does remind you of the rabbit. Let me go back to what the rabbit really looks like. You see triple points with angles coming in. Now let's go back to that and see triple points. This looks really quite a bit like some point of the rabbit, and I can make it look more that way. There it is, drawn with external angles. The same picture. Now we can take a look at the external angle that comes down to this point and observe that we see, for instance, yellow, yellow, red, 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 and so forth. We are seeing that same angle 1/7, which we saw over here. red, red, green, red, red, green, red, red, green, we're seeing the same combinatorics. But this whole thing is perhaps very puzzling. For one thing, out at infinity of C, we're measuring an angle in some sort of a circle at infinity. What circle at infinity can there be in C2? And the answer is there is no circle at infinity at C2. What there is at infinity is a solenoid. There really is a solenoid out there at infinity, and this external angle that you're seeing here is not measured in a circle. It is measured in the real line, which is the unique fixed component, path component of the solenoid. And you really are measuring an external angle in a path component of a solenoid, and you can measure them in other components if you wish. So there is a description of objects that I'm building in the dynamical plane in terms of external angles and identifications of external angles. And there even is a drawing of something that's happening in the parameter space. Something which looks a little bit Mandelbrot-y. And it's clear, if you look at this picture that you got by clicking someplace in the black, or this picture, which you get from picking out someplace in the colored locus, that there is I'm clearly drawing something significant. There really is a difference in character between these pictures. This looks quite a bit like a Cantor set, and the previous one looked quite connected. Now, I don't want to make the claim that this really works. It doesn't quite work. But next time, I will describe what this program is really doing. I will describe exactly what solenoid is sitting at infinity, and how to construct the whole behavior at infinity for Hinol mappings, including there's not just one solenoid at infinity. As it turns out, there are two solenoids at infinity. There are external rays going to one and external rays going to the other, and they have to meld in some particular way. And I'm sorry to say, I don't understand the compatibility relations between melding one way and melding the other, but understanding that is my idea for how we should try to understand Hinol mappings. Then I will continue, but that will presumably be the lecture afterwards, about the structure one sees at infinity for Newton's method in two variables. This is immeasurably more complicated, but quite entertaining also, in the sense that the pictures that one creates are sort of combinatorial models for the KAM theorem, with infinitely many tori associated to irrationals and all sitting inside each other with more zones of order and zones of chaos and so forth in between. And they are created by something which I call the Fari blow-up. And in my final lecture, I will try to show how these objects, the Fari blow-ups, and the infinitely many blow-ups that go to creating the solenoid, can be used in higher dimensions to understand the compactification at cusps of Hilbert modular varieties of dimension greater than 2, generalizing the work of Hirzebruch from the 1970s for Hilbert modular surfaces. And I guess I'll start here.
But in your the study of the Newton's method with this combinatorial KAM, is there any kind of underlying area-preserving dynamical system that might explain why it looks like KAM?
Undoubtedly there is, but I haven't found it. There must be. So the question was, I was announcing something which he knows well because he was at Cornell while I was developing all this. That the combinatorial structure of the sphere of infinity, when you're doing Newton's method in two variables, two complex variables, is a sort of combinatorial model for the KAM system, with tori corresponding to irrationals and zones of order corresponding, well, zones of disorder corresponding to the irrationals, was asking me, is there some area preserving map that this is associated with? And I was answering, I don't know. Yes? So what I have tried. What? So he says, when you draw three-dimensional drawings on a piece of paper, you don't draw slices. And I think implicit in his question is the fact that the mind has a remarkable ability to reconstruct three-dimensional objects from two-dimensional pictures, especially if properly shaded, and even more if they move in real time. So why am I making two-dimensional slices rather than at least three-dimensional slices, and perhaps changing three-dimensional slices to visualize four-dimensional slices? Maybe some kind of projections rather than slices. Okay, so there are various questions to this, one of which is that it's so much easier to draw slices. Another one is that I have actually never found three real-dimensional pictures very useful. And I recall having this discussion with Jack as to when we were particularly exploring cubic polynomials. The issue that, there the parameter space is two-dimensional, and one needs to try to understand its structure. And we made a lot of pictures, of three-dimensional pictures of that locus. And we never found them of any use whatsoever. It was always slices that turned out to be useful for us. Now, I don't really know why, but this is really almost as much a psychological question as a mathematical one, which is, to what extent is your mind capable of analyzing the three-dimensional pictures? There's no particular difficulty in creating doing the graphics is, well, of course it's not within my abilities, but it's within the abilities of my programmers. I can't do these kinds of things. Oh, and I really should say, the program that I've been showing here is written by a young man called Karl Papadopoulos, who was a senior at Cornell last year, and who is now a graduate student. He's lost to mathematics. He's a graduate student in computer science at Caltech. And he wrote this program, and he developed a lot of the mathematics, too. Okay, so it's almost a psychological question. I know how to do the computer graphics. I know how to find computer programmers who can implement it. But I do not know how to translate the pictures into useful information. Yes? How do I... So I told you exactly what you repeated. I think the question was, considering that the computers truncate everything, how can I use the computers to draw structure at infinity? Was that the question? Yes. Okay. Well, the point is that the behavior becomes quite regular at infinity. At infinity, some terms dominate the others, and in particular, the quadratic terms dominate the linear terms. As a result, near infinity, things simplify, and you can use just the coefficients corresponding to the dominant terms to describe what's going to happen forever. That is what I really did when I was drawing my external angles for quadratic polynomials. At some point, I decided that c squared plus c was going to behave just like c squared, and that I could ignore, as soon as z is big, c squared plus c is an awful lot like c squared, and I can ignore the plus c. But then it's easy to say what's going to happen under c squared, and that's what my computer program was doing. All computer drawings are an approximation. The question isn't to know, is the picture absolutely accurate? The question is, can you make an intelligent conjecture
on the basis of the pictures that you see.
Reproducible.
It's reproducible.
So that makes it valid.
I mean, it's absolutely reproducible. There is nothing even slightly non-deterministic about this. Yes?
When you build your combinatorial model of the mental project, it's naturally a limit of simple models, right? You start with 1 over 2 to the 1 over 3, 1 over 7, 1 over 3,
Yeah.
and so forth.
Yeah, the closure process doesn't seem... yeah.
The question is, do those intermediate finite models have any dynamical significance?
Maybe. 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 One really can wonder whether the complex, the Riemann spheres that you would build out of doing only finitely many of the identifications and gluing in disks in an appropriate way, which could be specified at the finite levels, converge to the Riemann spheres that you get in the limit. One really could ask that question, and I'm convinced that nobody knows anything about it. But I mean, it's very similar to the question of knowing exactly to what extent the combinatorics determine the complex structure. So you have to quantify that question to say to what extent the finite combinatorics approximate the infinite combinatorics. Hey, I'll think about it. I don't know the answer to that, but I'm convinced it's really an interesting question.
Yes? I just make one objection. I don't like this idea that a reproducible computation necessarily means anything. I mean, for example, you can look at the mapping x max to 2x modulo 1, simulate this in a computer, and you find that it always converges to 0. But this tells you something about the computer, not about the mapping.
Yeah, I tell you something about computer arithmetic, there's no doubt. No, well, it wasn't my assertion that it was reproducible. That was our noble honored guest. You know. I mean, my assertion was, can you extract something from the pictures which allows you to make conjectures that you can then prove? And the fundamental validity of a picture is, can you extract information, extract statements that can then be proved? That's my criterion for the validity of a picture. And I think you will find that the answer is yes. No, it is not possible. So I'm done.